The Yamanaka brothers Shoichi and Shigeru founded HOYA in 1941 during World War II. They saw an opportunity in optical glass industry which was critical for various applications. The foundation is what led HOYA to become the global company it is today. HOYA's expertise in material science significantly influenced its advancement in healthcare and technology, such as precise lenses and optical components in endoscopes. High-quality optical components for laser technology used in various industry applications. It facilitates the development of high-performance materials for electronics, including semiconductors.
It's hard to imagine getting through a day without being touched by semiconductors in some way. I mean, obviously things like computers, your smartphone, anything with the internet, but even things like agriculture. Nowadays, you use weather forecasts from satellites. There's robotic planters and harvesters, and even chips that are used to run the communications for remote areas of the world. Semiconductors are used in just about anything. As you want to make more and more sophisticated chips that do more and more, you need to get smaller and smaller lines. Traditional light that's been used to make chips has a limitation. The physics and the optics limit how small a line you can make. So once 193 nanometer became very difficult to go to smaller and smaller lines, a program called EUV, which are really soft X-rays, came into being. The wavelength for these soft X-rays is about 13.5 nanometers. So from 193 to 13.5 was a big jump, much smaller wavelength, enabled you to make much smaller lines and kind of break through the 7 nanometer limit, which the traditional light had. That really changed the game because some of the more complicated, sophisticated things people wanted to do required chips with lines of 7, 5, 3, 2, even down to below 1 nanometers, and EUV is required for that. In the old days, a blank was really for making a mask that was like a stencil. It either allowed light through where you wanted it to go through, or it blocked it where you didn't want it to go through. But at 13.5 nanometers for X-rays, you can no longer use a stencil. It needs to be a mirror. And that mirror has to be very sophisticated to be able to reflect X-rays, again, where you want them, and absorb them and not reflect them where you don't want them. So blanks are essentially what you build that mask, that mirror on.
The production of EUV blanks is highly demanding due to the needs of extremely precision, specialized materials, complex coating process, and highly controlled environment. Achieving atomic level surface smoothness is essential to avoid the reduction of reflectance due to the scattering of EUV light.
It's a very high-tech piece of quartz, and when I say high-tech, it's about 6 inches by 6 inches, 152 millimeters on the side. If that was the size of the Earth, it has to be so smooth that the highest peak would be no bigger than a single snowflake. That's the type of tolerances and dimensions we're talking about. So it's very complicated. About 5-6 years ago, the industry woke up and said, we really need EUV to keep our semiconductor technology roadmap progressing. We then made the largest capital investment HOYA had ever made to that point and bought equipment. We had to expand building, hire engineers, and lots of hard work.
We had to push the boundaries of metrology to see imperfection at the nanometer scale. Then we categorize the defect based on characteristics like size, shape, composition, and location to understand their origin. Our R&D process is different from our competitors because we adopt a dual location strategy with development activity in Nagasaki and Singapore to take advantage of both their strengths.
Each team brought their own strengths to the equation, and the combination of them was actually a spectacular success and enabled us to really leverage a new business opportunity for HOYA.
HOYA's commitment to R&D has been key to our success in semiconductor industry.
We have been the world leader in optical blanks, And because of that investment, we are now the world leader in EUV blanks as well. So it's been a good bet for us. Even though we're talking microscopic and even atomic level kinds of things, craftsmanship becomes even more important. And they contribute to very complicated, complex systems and products that help people do things like get better healthcare, see better. They enable all the internet and smartphone communications, the satellites. So it's a wide range of things that are either very directly helping people or helping establish products that help people. Every year, people ask, what's next? What's going to happen? How are we going to go over the next challenge? How do we make resist illumination techniques? How do we measure what we're making to tell if it's any good? How do we deal with the small lines that are only atoms wide? Those are the challenges that in the past, people would have said, well, there's no way we would have ever gotten to what we have today. But we have. It's very exciting. Just when people predict that the industry can't go any further, it goes further, and we're going to continue that path.